Section 3.2, logarithmic functions and graphs. So we're just going to set up an xy table again with this one, just like we did with the exponentials. It's going to be a little bit different, not a huge amount, still the same idea of choosing right around the origin and figuring out what the mother function is embedded in our g of x. So I'm going to go ahead and set this up in our form by factoring out the 2, and I'm going to set up my xy table. And then we'll talk about what the mother is. Okay, so I have my equation now set up in our form. So I took that negative out in front and I actually wrote it as a times -1, so we could see that that's actual multiplication to the y's. Factored out my 2, and then just brought down my +1. So from here, I want to take a look at what this mother function is going to be. And I know it's going to be the log base 3 of x. Everything else that's in there is a transformation. So if I go back to my table over here, I already have my table set up, so this is going to be log base 3 of x is equal to y. So I still want to be able to hover around the origin, but in this case, I'm not going to plug in x's. If I tried to plug in x's -2, -1, 0, I have major issues with those three immediately. You can't find log of a negative number, and you sure can't find log of 0. So, but I still want to use those values. What I'm actually going to do is I am going to let those be my y's. So if I plug in -2, -1, 0, 1, 2 to my y's, then we're just going to work backwards a little bit to be able to get the x values that go with it. So taking a look up here at my function, I want to rewrite this so that it's x equals. So this is actually going to be 3 to the y is equal to x. So what I'm going to do is I'm going to use those y's as my exponents. Again, I'm going to go down to the +1 again just because I think it's easier. So it's going to be 3 to the y. That's going to give me the x value that corresponds with this. This is going to be 9. So what this is it's the reverse, basically, or the inverse of the exponentials that I used previously. So on my exponentials, I chose x's to be -2 to +2 and found the y's. For my logarithms, I'm going to choose my y's to be -2 to +2 and then calculate my x's. So take a second, let's fill in the rest of this table. So with my table filled in, now I did my negative exponents after I did my positive, so I could just do the reciprocals again. Now, let's go ahead and just fill in the table. So now would be a good time for you to pause. I'm going to set up my x and my y, and I'm going to fill in the first part of the table with the multiplication and the division. So pause me now, see if you and I match. So my first table is going to show that I'm going to take my x's and divide by 2. It looks like multiply by 2, but with my x's I always do the opposite, so divide. Then with my y's, I've got that -1 on the outside, and I'm just going to do exactly what I see. It looks like multiplication, so I'm going to multiply. Remember that when you divide by 2 and you have a fraction, you're just multiplying the bottom of the fraction by 2. So dividing by 2 is the same as timesing by a half, which is how I got the 1/18, the 1/6, and then the 1/2, the 3/2, and the 9/2. Should be fairly obvious as I'm just dividing by 2. And then timesing by -1 flips all of the signs. Now, on the next thing, what I want to do is be able to add 2 to my x's. What you can do is you can get a common denominator right now if you think it's going to help, or just add 2 to them. I think I'm just going to add 2 because it doesn't seem like that. It doesn't seem like it's going to be too bad. And then with my y's, do what you think. Pause me now and see if you and I match. Okay, so I have my final table in the transformation. I still need to pull it together at the end, but take a look. These are the exact same values that you should have at your final result after performing all of the multiply, divide, add, subtract. So let's go ahead and write the full table together and set up our axes. So now I have my final table set up, and I have my axes already set up, so let's go ahead and plot these points. I don't think I want to do the 2 and 1/18. Let's start at the 2.5, 1. Let's see if that'll give me enough information. So make my increments at 1 again. So if I go 2.5, 1. What else do I have? 3.5, 0. 6 1/2 negative 1. Doesn't look like too much, so I guess I have to graph the other ones. So 2 1/6 is going to be 2. Actually, I think I'm happy with that one. So I do kind of see that curve that I get with logarithmic graphs. But before I sketch this, I want to identify my asymptotes. So if I take a look back at my original function, let's write that down here so we've got it to look at. I know that with logarithmic functions like this, I'm always going to have a vertical asymptote. The reason why it's a vertical asymptote is because with logarithms, there's always going to be a restriction on the x itself. And actually, I think I want to rewrite this in our form, so let's fix that. There's always going to be a restriction on the x's because, think about the properties of logarithms that you know, you're not allowed to take the log of a negative number, you're not allowed to take the log of 0. Once you get past 0, though, you're fine. So it's whatever makes the inside here 0 is where you're going to have a vertical asymptote. So this shouldn't be too bad. If I take a look at it, and if I set that equal to 0, using what I know from Algebra 1, I know that this is going to give me x equals 2. And that's actually your vertical asymptote. It's whatever makes the stuff inside in the logarithm 0, because that's your cutting point. You can't be 0. You can be super close to it, but you can't actually be there. So going back to my graph over here, I think I'm going to have my vertical asymptote at x equals 2. So let's put that in, and then I'm going to feel a bit more comfortable being able to sketch this thing. And that does give me the boundary that I was looking for. So again, nice smooth curve. And try to connect the dots. So same idea with the previous set of notes. We have our sketch. We're going to be able to identify all the other stuff that goes with it, with the transformation. But let's go ahead and do the domain and range. So the domain this time, there is a restriction. If you take a look at the graph, it's going to start super close to 2, and then it's going to take off to the right to infinity. The range, though, there's no limitation this time on the range, not with logarithms. So with logarithms, domain is restricted because of the vertical asymptote. Range is not. So this thing's going to be as high or as low as I want it to be. So x-intercepts y-intercept. Well, I think the easiest one is probably the y-intercept. Based off of the location of your vertical asymptote, you don't have one of these. It's never going to hit because it's not going to go past that x equals 2 line. Your x-intercept, again, we could plug in y equals 0 and solve, but I don't need to because I have the point. If I take a look back at my table that I did, I'm looking for a y value of 0. I think it's at the 3.5, 0. Now, same idea though. If that wasn't given to you, plug in 0 for y and solve. Alright, now with the transformation itself. So taking a look at what we did. The first thing that we did was we took our x's and we divided them by 2. So that means that distance between two x values is being shrunk. So this is going to be a horizontal shrink. Oh, and I wasn't as specific as I should have been in the first set of notes. My apologies. Whenever you say that it's going to be a shrink or a stretch, you need to say by what the factor is. So back in the 3.1 notes, you need to identify what the shrink or the stretch was. So in this case, we want it to be a horizontal shrink or compress by a factor of, and we actually shrunk it by a factor of 2 because we divided by 2. All right, then with my y's, I times by -1, which means I had a vertical reflect. The 1 didn't do anything, but the negative sure did. Then, with my x's, I wanted to add 2, which means I slid them to the right. And then with my y's, I added 1, which means I forced them up. So again, quick clarification on that, sorry, back on the first set of notes that we did. Whenever you talk about a shrink or a compress, it make sure that you talk about what the factor is. So, like, what did you do to it? So was it a shrink by 2? Then that means that you divided by 2. If it was a compress by 5, remember compress and shrink mean the same thing, so you divided by 5. All right, let's take a look at the next slide. So we have another problem just like this, and I'm not going to do as much talking through this one. I am going to set up different pieces and just pause, and I'll tell you where I would pause if I were you to see if you can match up. So what I'm going to do right now is I'm going to put this in our form. I'm going to identify the mother, and I'm going to create the mother points. The next time that I unpause, all of those will be on. So if I were you, I would stop it now and see if you and I match. Okay, so I've rewritten it in our form, factoring out the 1/3, and then I identified my mother, highlighted it in yellow, and I went ahead and set up my table. So this is what your first set of work should look like. Now what I'm going to do is I'm going to set up the second table. So I'm going to set up the operations, and then I'm going to go ahead and fill them in. So again, now would be a good time to pause and then see if you and I match. Okay, so with my x's, it looks like I am going to be dividing by 1/3. So I could have written that, but I know dividing by 1/3 is the same thing as timesing by 3. So I decided to write it as timesing by 3. They're exactly the same thing. And then with my y, I'm going to times by 1/2. So I take a look at my entries. This is what your next table should look like. Now, again, I'm going to pause. Now would be a good time for you to pause as well. I'm going to set up my last table, and then hopefully we match. Okay, so now I have my final table. So with my x's, I needed to add 3. So I went ahead and just add 3 to the previous entries, and then to my y's, I needed to subtract 2. After doing that, I went ahead and set up the final table over there for my mother being mapped to my g of x function. All right, so we need to graph this. However, with the previous ones, I went ahead and just started plotting the points. I actually want to see if I can do the vertical asymptote without actually doing that. So first, I want to get the vertical asymptote to help myself out. So I'm going to rewrite my function down here, just so I can take a look at it. It's going to give me, again, in our form, so I'm going to go ahead and pull out that 1/3. Just like I did with my transformation. And then I'm going to look inside. It's whatever makes that 0 is where my vertical asymptote's going to be. And I don't really need to do any work. I know that the 1/3 kind of gets ignored. The vertical asymptote is just going to be x equals 3. Now I'm going to go ahead and sketch this. So again, pause, see if you and I match. Okay, so here's my sketch. I did neglect to put in the last point of 15, -1, simply because I knew I was going to run into my writing on the right-hand side. So I have enough points here, and really the whole idea of the transformation is just get enough points so that you can see what this thing is supposed to look like. So I have my vertical asymptote. Now I can take a look at the behavior of the graph and tell you that the domain is going to start immediately after 3 and head off to infinity. The range, again, no limitations on the range here. Y-intercept, doesn't look like there is any, so it's not going to go past that vertical asymptote. My x-intercept, though, I do need to find, so, because it's not in my table. So what I'm going to do is I'm going to go back to my equation, do it over just underneath my graph here off to the side. So I'm going to do 0 is equal to, I've got my 1/2 log base 2. I'm just going to go back to the original form, 1/3 x minus 1. Not that it matters. Minus 2. Okay, let's manipulate this thing. And it better have an x-intercept because this graph is growing. It will eventually hit 0. All right, so I think I'm going to add the 2 over, and then I'm going to get rid of that half as well. So if I add the 2 over, I'm going to get 2 is equal to 1/2 log mess. Then I need to get rid of that -1/2. So to divide by -1/2 is the same thing as to times by 2. So I think I'm actually going to get 4 over here. And then just bring everything else down. Rewrite it. So I'll do my 2 to the 4th, which is going to give me 16. So this is just that property of rewriting logarithms into exponentials. and then just bring down the stuff inside. Add the 1 to the other side, and then times by 3. So timesing by 3, I think it's going to give me 51. Alright, so it's way out there. So my x-intercept is going to be 51, 0. But it worked out actually pretty nice. I mean, it's a large number, but it's pretty nice. Alright, let's go ahead and explain this transformation. So the first thing that we did to our x's was we times them by 3. So that means that this is between the x's, that's horizontal, and timesing by 3 is going to stretch them. So, and then we need to be clear here. So by a factor of, and we times by 3, so by a factor of 3. Then with our y's, we times them by a half, which shrunk them. So this is going to be a vertical compress or shrink. Either is fine. And this is going to be by a factor of 2. Since we took all of the y's and we shrunk them in half, so by a factor of 2. Then with my x's, it looks like I added 3, so I slid everything to the right. And then with my y's, I subtracted 2, so I went down 2 units. Okay, so there's our second one. Okay, bit of an application problem. So they're given an exam and then tested monthly with an equivalent exam. Average scores for the class modeled by that equation, where t is the time in months. So it was the average score on the original exam when t is equal to 0. So let's just plug in t equals 0. So I want to find f of 0. So everywhere I see a t, I'm going to cram in a 0. So I get 80 minus log base 10 of, plug the 0 in, and I get 0 plus 1. Now there's a couple ways that you could do this. If this was on the calculator portion of the test, then you can just grab your calculator. If this is on the no calculator portion of the test, then you need to be able to use your properties here. So I know that 0 plus 1 is 1. Using what we know about being able to do the logarithmic graphs on the 2 previous slides, I know that if I can get this 10 and this number to match, then I get to use that really cool property of logarithms, in that if the bases there match, the logarithm and the exponential cancel completely, and all I'm left with is the exponent. So I think that's what I'm going to do, because just in case this was on a no calculator portion of a test. Chances are it could be on either, so may as well practice. So what I want is I want to get 10 to some power that gives me 1. So from here to here, I'm doing 10 to some power gives me 1. Well, the only power that's going to work there is 0. So 10 to the 0 power is going to be 1. Now, here's when the beautiful happens. This 10 and this 10 both match, which means if you have a logarithm and an exponential with the same base, they knock each other out. So all I'm left with here is f of 0 is equal to 80 minus, bring that exponent down, 0. So, looks like it's going to be 80. And then taking a look at the question, it says what were the average score? So, does it say that this is percent? Doesn't say what it is. So, I would say the average score is 80. So that's going to be the points for this one. Taking a look at B, it was average score after 4 months. All right, T is time in months. All I have to do is plug in 4. So let's do the exact same thing. So I'm going to do f of 4, plug a 4 in for all of my T's. So it's going to give me 80 minus log base 10 of 4 plus 1, which is going to be 5. Now without a calculator, I would say you'd stop here, but this context doesn't really make any sense. So at this point, grab your calculator, type this in, see what you get. That's going to be the answer to this question. And keep in mind that your calculator is programmed with log base 10, so although I wrote the 10 here, it's really not necessary to do that. When I plugged this in, I got 79.30103. So I would say that the average score then was 79.301. Okay, on our next slide we have two more parts. Let's go ahead and fill these in. Average score after 10 months. Do the exact same thing, just plug in 10 this time. So previously we've plugged in 0, we've plugged in 4, now we're just going to plug in 10. And just follow the exact same steps that you've been following. Type it in your calculator. It looks like 78.9586. All right. Verify your answers using a graphing utility. Okay, well, we partially did that because we were typing it in as we went. Another thing that you could do is you could actually go to your Y1 button and type in the equation, and then you can just use the table feature. So what you could do, just hit your log button. It'll automatically do log base 10. Hit your xt theta n button, and then from here go to the table. And for the first one, all we would want to do is look at what you get when x is 0. Then for the second one, we would look at when x is equal to 4. And then for the third one, we'd look at when x is equal to 10. And you should be able to read these values off of your table.